The next method is by parts. Method 3, by parts. Integration by parts. This one, you will be given an integral of the form u dv. So whatever will be given as a question, you separate. It will be a product. So call the other guy u, and the other one you call it dv. The one you choose to be u, you must be able to differentiate it. The one you choose to be dv, you must be able to integrate it. Okay. So let's do. I demonstrate now. So if we have an example for you to see proper. When you choose like this, then you look for v multiplied by u, and then subtract v multiplied by du. Examples. Evaluate a, the integral of x multiplied by e 2x dx. Very, very simple question. So you said, what you let you must be able to differentiate. So let u be equal to x, so that when we differentiate, it will be 1 dx. Then let dv be equal to e 2x dx, so that when you integrate, you get v is equal to 1 over 2e 2x. In this case, you don't introduce c when you integrate dv. And then fit them in the formula. So I'm saying the formula is, if I had u dv, my integral is going to be uv minus v du. So we had x e to x dx. The integral is going to be u is x, v is half e per x. So I'm going to have half x e to x minus the integral of v e to x dx. This is half x e to x minus, you can bring the half outside and then integrate e to x, which is going to give us half e to x. That's why now introduce a c because we are done integrating. This is going to be half x e to x minus 1 over 4 e to x plus the constant c. So here what we have done is that we've taken the half outside and then remained with e to x inside. Then the half is still outside as you integrate e to x. So we still get half and then e to x. So then those two multiply, so we'll have 1 over 4. Another example, the integral of x squared ln x dx. Here, if you let ln to be your dv, you can have serious issues in integrating it. So you let u to be your ln x, because its derivative du dx is as 1 over x. So cross multiply to solve du, you get 1 over x dx. Then let dv be x squared, so that when you integrate, you get v is equal to x3 over 3. Then now you put in the formula x squared ln x dx is going to be uv, which is x3 over 3 ln x minus the integral of v, which is x3 over 3 multiplied by du, which is 1 over x dx. This is going to be x3 over 3 ln x minus the integral of 1 over 3 x squared dx. This comes out to be x3 over 3 ln x minus x3 over 9 plus c over 9, because when you integrate x squared and there's a 3 outside in the denominator, we're going to have 1 over 3 x3 over 3 is going to be x3 over 9. That's a thing. So that whenever you have a combination of polynomials multiplied by logs, the logs are what you let to be u, and the polynomial to be a dv. So note that whenever whenever you have note that whenever you have the integral of xn ln u, I will just say xn ln x dx, let u be ln and dv be xn. Here, for this case, whenever you have the integral xn e x dx, let u be xn, and then dv be ex, so that this one should be reducing, because the other guy is going to be fixed. The ex will keep coming back. Another question.
Sir,
Hello.
yes, sir, I do not understand there how you found x cubed over 9.
Integrate x squared. What do you get?
It's x cubed.
What?
over 3.
Then multiply by 1 over 3. Okay. Another one. Another method. I know we still have more on by parts, but let me bring up another method. Partial fractions. Partial fractions. We'll go straight into examples. Integrate a 2 over x minus 1 x plus 2 dx. When you find such a question, the first thing you do is to look for the partial fractions of this function. Say it will be a over x minus 1 plus b over x plus 2. And then multiply throughout by x minus 1 x plus 2. So you get 2 is a x plus 2 plus b x minus 1. Then when x is equal to 1, we'll have 2 is equal to 3a, giving us a is equal to 2 over 3. And when x is equal to negative 2, we'll have 2 is equal to negative 3b, giving us b is equal to negative 2 over 3. So now I'll come back here and say, this is the same as the integral of a is 2 over 3 minus b is 2 over 3. This whole thing dx. So the 2 over 3 can go out as we remain with 1 over x minus 1 dx minus the 2 over 3 can go out as we remain with 1 over x plus 2 dx. Then now, since we saw that whenever we differentiated ln x minus 1, if this was f of x, and they tell us to find the derivative of this, you differentiate x minus 1, you get 1, and divide by x minus 1. If f of x is ln x plus 2, the derivative of this, you differentiate x plus 2, you get 1, and divide by the whole x plus 2. So here we have 2 over 3 ln x minus 1. So remember that ln does not take a negative number. So you emphasize that it must always be positive by putting the modulus minus 2 over 3 ln x plus 2 plus c. So we go back in reverse. When integrating, you're looking for the function whose derivative is what you're integrating. So since our derivative is 1 over x minus 1, the integral should be in x minus 1. And it will work very, very well, because if you remember very well here, we said that the partial fraction should always have a difference in terms of the powers of x be 1. So substitution then will be working in some cases. Where substitution cannot work direct, ln will come in to help out the situation. So these are the 4 methods of integration that we have in this course.
Please quickly go through the one for partial fractions.
Here where we are?
Yes.
Okay. So from this, since we have linear denominator, you split a over the first linear, b over the second part, and then multiply throughout by this guy, so that this can take away that, this can take away x minus 1, and you remain with x plus 2. So to multiply a, x plus 2 take away x plus 2, so you have b multiplied by x minus 1. Then when x is 1, you have 2 is equal to 1 plus 2, you get 3. 1 minus 1, 0. So you have 2 is equal to 3a. When x is -2, you have -2 plus 2, 0. So all you want is that one variable must disappear so that you can find what remains. So you have -2 minus 1, -3. -3b is equal to 2. After you get your a and your b, you take them here. Bring a here, bring b here. But remember, you got this thing on the integral. So you bring it back, the integral. And then you take the constant out as you integrate 1 over x minus 1. The constant out as you integrate 1 over x plus 2. And then this 2 over 3 remains here. Ln x minus 1. Since we have seen that the derivative of ln is just the derivative of the x minus 1, which is 1 over x minus 1. So whenever we find 1 over x minus 1, whenever you find that the derivative of what you're looking for, when do you use ln? When you find that you have the derivative on top and down you have the function u. Okay? When you find that your du is the numerator and your u is the denominator. This u down here, for you to use a ln, must not be to any power apart from 1. When you find such a situation, the integral is going to be ln u plus c. But if you find that you have du over u power n is no longer ln, this becomes u negative n du. When n is 1, the reason why we use ln is because when n is 1 and you want to use extended power rule, this is the same as x power -1 dx. So if you try the addition rule, you are going to get x power 0 over 0, which is undefined. This is the reason why ln comes in to help out the situation. The next example is, so this was example A. B, away from partial now, the integral of x over the root of 3 minus x squared dx. How do you integrate such a function? So you say, okay, let u be √3 minus x squared. Then du dx is equal to negative 2x. If we solve for dx, we'll get du is equal to negative 2x dx. That is, you divide by negative 2x, divide by negative 2x. So that we get dx to be negative du over 2x, giving us the integral of x over u negative du over 2x, which is equal to negative 1 over 2 du over u. Since this x and that x will cancel. So now we have negative half ln u plus c. Since we said that whenever we have such a situation, we resort into a ln. So we have negative 1 over 2 ln u is the root of 3 minus x squared plus c.
I said, when do you use the modulus?
Just to indicate that whatever is inside ln must not be negative, because ln of negative is undefined. So all these integrals that you have done are called indefinite integrals. The integrals without the limits on the integral side.
Yeah.
Hello?
Okay, can you just try this one?
Okay.
Can I take the integral of the square root?
As a numerator or standing alone?
Inside the square root is a fraction.
Okay.
X plus 3 divided by x cubed.
Divided by x cubed dx. Simplified as the root of 1 over x squared or before this one, simplified as x plus 3 over x squared multiplied by x dx. So the x squared will pop out as x and then x plus 3 over x dx. Like that. And then let's see, if we let u to be what is inside, x plus 3 over x, what is the derivative of u? It's going to be, this is the same as 1 plus 3 over x. So the derivative is going to be -3 over x squared, which is not anywhere outside. So we can't use the methods that are known. And using also by parts, it won't work well because of the root. So you need an external method that we haven't looked at yet. So for now, suspend it.
Yaba Chimone Njuga.
Okay, so what is remaining is to look at the combinations.
Hello.
Huh?
Sir, so for
Hello.
the first one, did you say U is
I can't get you.
sir, yes, I was asking for the first example. What did you let U?
We say that whenever the difference of powers of x between the numerator and the denominator is 1, the one with the higher power is what we call u. And then when you differentiate it, we'll have the one with the less power. So I wanted to bring in the issue of definite integrals. These are indefinite integrals, the ones without limits. When you say limits, we mean integrals running from a to b of f of x dx. The integration will be the same, except that when you find your answer, f of x, then you bring back your limits and say, I will substitute b first in the integral, then subtract the one where I'll substitute a. So this will be a constant. And this constant is called the area of the region under integration. Where you are given some region, you have a shape of this nature, and then you get your a to be this part, your b to be that part. When you get the integral, we are saying that you are finding the area of this region here. If you want you to run from C, then you do the addition and also get the area of the integral from here. So you have an integral from C to B of f of x dx, which you will split as from C to A of f of x dx, and then add from A to B of f of x dx. So this is what is going to be our next session tomorrow. So look at definite integrals, and then of course we've done a few examples on by parts. So we'll have more of the by parts coming, and then we'll use the limits on them, even as we extend the limit issues to other questions. And then we look for special cases of integral That needs either a combination of all the methods or trig substitution, which is not done mostly in first years. Like for this function. Okay, so we'll meet again tomorrow. Good night.
Good night.